Kirchoff's first law is that for any junction, the sum of the current is equal to 0. So that means that the current coming into the junction is equal to the current leaving the junction. We haven't gained or lost any current. And we can use this equipment here to explore the meaning of Kirchoff's law and specifically how it works with current in a series and a parallel circuit. So I'm going to start off by putting in a power supply. So here's our power supply. There's the positive is the longer line, the shorter line is the negative. And what we can do is we can connect into this circuit a lamp. So let's put a lamp in here. And the lamp is lit now, and what I want to do is I want to check that the current going into this component, the lamp, is the same as the current leaving the lamp. So let's just use an ammeter. So here's the ammeter, and I connect that into this circuit. And it tells me that the current going into the lamp is 0.11 amps or 0.12 amps. And if I switch it on the other side, the current leaving the circuit is 0.11 amps as well. So in this arrangement, Kirchoff's law has been proven. So the current going into the lamp is equal to the current leaving the lamp. What I'm going to do now is I'm going to replace this lamp with, this wire with another lamp, and so the current leaving now is 0.07, it's smaller. The lamps are dimmer, and so the resistance has increased because we now have two lamps in series. So the resistance is increased, the lamps aren't as bright, and the current has gone down. And if I change this over, let's just check the current going in, and the current going in is 0.07 as well. Finally, what I'm going to do is I'm going to add a third lamp in there, and we'll just have a look at the effect of that. So again, the lamps are even dimmer again because I've now got three lamps in series. So I've increased the resistance again. The current is smaller, 0.06 amps going in, and I can prove Kirchoff's law if I check that the current coming out is the same as well, and it's 0.06 coming out. So Kirchoff's law is that the current isn't lost. The current going into a junction is equal to the current coming out, and we can see that in this arrangement that is definitely the case. So we're still looking at Kirchoff's first law, so that the sum of the current at any junction is equal to 0, so the current going into the junction is equal to the current leaving the junction. And what I'm going to do now is see whether that applies for a parallel circuit as well. So we'll start off, as we did before, with just a single loop. So here's our single loop, and the current entering and leaving this junction should be the same. So I can test that out if I put my ammeter here. Don't worry about the minus sign, that just represents the direction that the current's going, but it's between 0.11 and 0.12, and that is equal to the current coming back here, 0.11. Now what I'm going to do now is I'm going to add another loop into the circuit. So I'm going to add another lamp in parallel now. So there are now two routes for the electric current to take. And what Kirchoff's law is saying is that the current at this point coming into the junction is equal to the current leaving the junction. So some of the current's going that way, some of the current's going that way. And what we should just establish is the current that's coming into the junction equal to these two currents that are leaving the junction? So we'll just put an ammeter in here. So the current that's coming into this junction is 0.2 0.21 amps. And the current coming in this direction is 0.10. So that would tell us that the current going through this lamp should be 0.1, 0.11 as well. So I've just rearranged the circuit so that I can put an ammeter in here. So this was 0.21, this is 0.10. So we should just check the current at this point here. And the current here is 0.11. So 0.11 plus 0.10 should add up to the current here, and it does. So we've got 0.21 going in and we've got roughly 0.2 coming out. So the current is the same at this junction. So what we're saying effectively is that the current comes along here. Some of the current goes in this direction and some of the current goes in this direction. Now what I could do is put another lamp in this branch here. The current overall has gone down, so 0.17, but that is because the resistance in this branch has increased. The resistance in this branch is still the same. So if I connected the circuit here, I would expect it to still be around about 0.10. So it is 0.09, 0.10. So it's very, very similar. What I've changed is the current in this branch here. So I've changed the current because I've increased the resistance. If I put another lamp in parallel, like so. So I've now got 3 lamps in parallel, and again what I want to do is check what's happening at each junction. So let's look at this junction first of all. So the current going into this junction is 0.31 amps. The current going down towards these 2 lamps is 0.20. So at this point I've got 0.3 amps coming in and I've got 0.2 heading in this direction, which should mean then that the current here should be my missing 0.1 amps, and it is. So if I add the current here going along this branch to the current heading this way, that adds up as expected. So this is 0.2 and this is 0.1. So that tells us that Kirchoff's law is correct. And our general rule is that the current in a parallel circuit, the current in each branch adds up to the current leaving the power supply. So I have 0.1, 0.1, 0.1, and I've got 0.3 leaving the power supply. And then when it comes back together, so I've got 0.3 going down here, 0.1 heads off on this route, 0.2 comes to here. 0.1 goes this way, 0.1 goes this way. They come back together, so I've got 0.2 here. And then it's joined by another 0.1, so I've got 0.3 here. So I have 0.3 leaving the power supply, 0.3 joining the power supply.